Hello, my friends. The NOLA Mathman coming again for another fun math adventure. Unlike Superman, I cannot leap tall buildings in a single bound, and I'm not faster than a speeding bullet. But in regards to math,
Superman got nothing on me.
After watching this video, students will be able to solve problems using the Pythagorean Theorem. The concept we're looking at is radical functions in geometry, and the skill we're looking at is the Pythagorean Theorem. So with no further ado, let's get started with our video. So in this first problem, we want to use the Pythagorean Theorem to find the sides of right triangles. That's when you use the Pythagorean Theorem. So we're finding missing length. First thing you do is label the sides as given. The shorter side is usually A. The middle side is B. We set those equal to A and B. We're looking for the hypotenuse C. So we substitute in the equation. Pythagorean Theorem is A squared plus B squared equals C squared. We substitute A and B. We have 21 squared, which is 441. 72 squared. Get your calculators. Takes a minute here, so no math man is working. It is 5,184, and that will equal C squared. So when we add the two sums together, the A and B, A squared and B squared, we're left with C squared. I move it over to the right left so that we can solve for C on the left. So that equals 5625. We take the square root of both sides, the inverse of square to get C. And so C will equal the square root of 5,625, which is 75. So the longest side, C, will be 75 in this problem. So again, the way the Pythagorean Theorem works is we have three sides of a right triangle. We substitute two of the sides in and solve for the third side using that form. So we're done with number one. We'll proceed now to another right triangle where we're trying to find the sides. So again, the more you do these, the more comfortable you'll get with the Pythagorean Theorem. It's a very important formula that you will see throughout geometry and into Algebra 2, Calculus, all those higher level maths. So again, we'll do another example. Number 2 now shows up on the screen. We have the B term given. We're looking for A, and this time the hypotenuse is given. So we're not looking for C, we're looking for a different term. So we want to label the sides as given. 39 being the longest side of C, since normally A is going to be the shorter side, but since they made the middle side A, we set 15 equal to B. It doesn't matter which one A and B is. I typically like to set the lowest one equal to A, but it doesn't have to be that way, as you can see in this problem. So we substitute 15 for B, we substitute 39 for C, and now we plug it into the Pythagorean Theorem. You always want to write that formula at the start, A squared plus B squared equals C squared. We substitute B and C in, we're left with A squared. 15 squared is 225, 39 squared is 1521. To get A squared, we must subtract 225 from both sides to get rid of that. Now we have A squared by itself. We get that equal to 1,296. To solve for A, we take the square root of both sides because that's the inverse of squaring. And we're left with a value of A. And again, you gotta get your calculators. It's equal to 36. And so the A side will be equal to 36, which is smaller than the hypotenuse, I'm sorry. The two large sides or legs have to be shorter than the longest side, the hypotenuse. So you always want to check that. And since 36 was smaller than 39, we know that that solution can work. So that's always what you want to do when you check your sides of a right triangle. So now we'll do another example here. We'll do number 6. And in this problem, we're given two sides of the right triangle, two of the three sides, and we solve for the missing side. So we want to label the sides as given. B is going to be 240 because it's one of the legs. The hypotenuse is always C, so we set C equal to 250. We write our formula for Pythagorean Theorem. A squared plus B squared equals C squared. We substitute for B and C, and we solve for A. So that's what we do. So after we substitute in, we're going to square 240 squared, we're going to square 250, and we're going to get what that equals. So again, you get your calculator out. You don't want to do this one in your head. 240 squared is 57,600. 250 squared is 62,500. Now, to solve for A, we have to get rid of 57,600 by subtracting both sides by that, because it's positive. By doing that, we get A squared, and that will equal 62,500 minus 57,600, which is 4,900. Now we take the square root of both sides to solve for A, and A is going to equal 70. And so, as you can see, that's our answer there. And that's what we get. So, we've done 3 examples of finding the missing side, and typically that's what you will use the Pythagorean Theorem for. So, let's see if we do any other problems where we need the missing length. We'll see in a sec here. We've done 3 of those so far. So we'll move number 6 out the way. And again, the more you do these, the more confidence you'll get in the process. Looks like we're done with finding the missing lengths of right triangle sides. And now we're going to do a different type of problem. So in this problem, the directions state we will determine whether each set of measures can be the sides of a right triangle, then determine whether they form a Pythagorean triple. So we get to learn a new concept. What is a Pythagorean triple? Well, we'll find out by doing some of these problems. So basically what it is when you plug in the 2 smaller sides, does it equal the hypotenuse squared? If it is, it's a Pythagorean triple. The key is they have to be integers. So in this first group, we're given integers. So we want to see if they are sides of a right triangle. We label the shorter side A, the middle side B, and the longest side C. We write down the Pythagorean Theorem as we've been doing. We substitute for A, B, and C. And we want to see if both sides of the equal sign will be the same. So we square 7. That will be 49. We're going to square 24. That will give us, again, get your calculators out, 576. And then we will square 25. And that will give us, I believe, 625. Now, once you do that, you have a sum on the left side of the equal sign. You add 49 and 576, and if that's equal to 625, then it can be the sides of a triangle, and we can determine if it's a Pythagorean triple. Well, yes, they are equal. So what does that mean? That means these 3 sides could be the sides of a right triangle. That's the first question we have to answer. And then determine whether they form a Pythagorean triple. The answer to that question would also be yes, because 7, 24, and 25 are all integers, and we know they form a right triangle, so they have to be a Pythagorean triple. And again, the NOLA Mathman is writing all this down. It is very important when they ask you questions in math that we write the answers in complete sentences as they ask you to do in Common Core. So that is what you see here on the screen. You want to write this as complete sentences as the NOLA Mathman is doing here. So you can see that there. So the answer to the question is yes, they can be sides of a right triangle, and they do form a Pythagorean triple. Very good. So in that problem, we had yes to both questions. So let's see if we can have a problem where it won't work out. So that's why we keep doing problems. So now we do number 9. Our sides are 16, 28, and 32. We label the sides accordingly. Shortest side is A, middle side is B, the longest side is C, We substitute it into a squared plus b squared equals c squared, and we see that both sides of the equal sign will be the same. And so when we do that, we have to square 16 squared. Again, get your calculators out. That equals 256. 28 squared. Again, plug it into your calculator, and you will get a value of 784. And then we will square 32. And that will give us a value of, again, let's look at it on the count, 1024. So now we add the two sums on the left side of the equal sign to see if they equal 1024. If they do not, it will not be sides of a right triangle. We will know that. Now the last one, they both were equal, so we had yes for that question. So let's see, get your calculator and add those up. And we will end up with 1040, which is not equal to 1024. Even though they're close, they have to be exactly the same. So this answer would be they're not sides of a right triangle. And if they're not sides of a right triangle, they cannot be a Pythagorean triple also. So that is, again, what we're writing down. Now again, we're writing this down verbally, but if we want to really scrutinize it, it was not a complete sentence. So the NOLA MATHMAN has to work on that. So now we're going to do number 10. We have the sides 18, 24, and 30. Again, we're going to use the Pythagorean Theorem to determine if they're sides of a right triangle. We label the shorter side A, the middle side B, and the longest side C, as we've been doing. We write out Pythagorean Theorem, we substitute for A, B, and C, and we end up getting 18 squared plus 24 squared equals 30 squared. So we will square each of those bases, and we will end up with 324. Again, you can get your calculator and get that answer quickly. 24 squared is 576, and 30 squared is going to equal 900. So it'll pop up on the screen in a second. And so once we do that, you will add 324 and 576 to see if that's equal to 900. And if it is, then we know these are the sides of a right triangle. So that does equal 900. They're equal. And so we can say that these three sides, 18, 24, and 30, are sides of a right triangle. And since all three of these values are integers, we can also conclude that these are, they form a Pythagorean triple also. And again, that will be written down here by the NOLA MATHMAN. And as you can see here at the bottom of the screen, we want to write this as a complete sentence. So we're done with number 10. Very good. And so now, so what's the example of a problem that you have the sides make up a right triangle, but they're not a Pythagorean triple? Because everyone we've done so far that has followed the Pythagorean theorem has also been a Pythagorean triple. What example would be where it's sides of a right triangle, but it's not a Pythagorean triple? Maybe the NOLA MATHMAN will do an example of that next. Let's try 12. So 12 is a little different because not all three of these sides are integers. We have 5, 7, and the square root of 74. Square root of 74 is not an integer. So maybe this will be the type of example we're looking for. So again, we write the Pythagorean theorem. We label the shorter side A, the middle side B, and the longest side is C. We substitute that into the equation for the Pythagorean theorem, and we want to see if A squared plus B squared is equal to C squared. So we square 5, that's 25, 7 squared is 49, square root of 74 squared is 74, so they're equal. So we know that these are the three sides of a right triangle. The question is, do they form a Pythagorean triple? Well, they don't, because the square root of 74 is not an integer. And so therefore, in order for it to be a Pythagorean triple, all three sides have to be integers or whole numbers. So we answer it can be the sides of a right triangle. That's true because a squared plus b squared is equal to c squared. But they do not form a Pythagorean triple because of the square root of 74 being one of the three sides. So that is basically what the NOLA Mathman is writing here. And yeah, there we go. Not an integer. There we go. So looks like we have done a variety of problems dealing with the Pythagorean theorem. We've learned how to label sides and substitute and find a missing side. We learned how to determine whether sides can be measured without the figure being shown. We've determined and found out what a Pythagorean triple is. And so we've learned a variety of different concepts, and we're now done with the concept of Pythagorean theorem. And until we meet again, another math adventure, this is NOLA Mathman signing off. Have a blessed and prosperous day.
Awesome stuff.